So for part 4, basic question 1, you have the Earth as a sphere and you have a person 600 kilometers above the Earth. They want you to find the the gravitational force on this person. So you have the mass of the Earth. It is 6.0 times 10 to the power of 24 kilograms. You also have the mass of this person with 80 kilograms. You also have you also have the radius of the Earth, 6.4 times 10 to the power of 3 kilometers. And you have a constant G, 6.67 times 10 to the power of minus 11 Newton meter squared over kilogram squared. So to find the gravitational force on the object, we use F equals G, the mass of the Earth, the mass of the object or the person, over the total R squared, which is all of this, so it's the radius of the Earth plus h, which is 6.4 times 10 to the power of 3 plus 600. So you put 6.67 times 10 to the power of minus 11 multiplied by the mass of the Earth, which is 6.0 times 10 to the power of 24 kilogram times 80 over the total R, which is 6.4 times 10 to the power of 3 plus 600 squared, and you'll get 653 newtons. So for part B, this object or this person is rotating around the Earth, and they want you to find the speed, the linear speed. So we can use net fx or net f equals ma, and from chapter 9 in the university physics book we know that a equals v squared over r, and this f from part 8 is equal to g m over r squared. So you do g times m over r squared is equal to m times v squared over r. If we solve for v, we'll get v squared is equal to g m over r. So we can use that formula. V squared is g m over r. So v is radical g m over r. G is 6.67 times 10 to the power of minus 11, and the mass of the Earth is 6.0 times 10 to the power of 24 over r, which is 6.4 times 10 to the power of 3 plus 600 radical all of that, and you'll get 7.56 times 10 to the power of 3 meters per second. Okay, so for basic question 2, you have the Earth. The radius of the Earth equals 6.4 times 10 to the power of 3 kilometers. You also have the mass of the Earth. It is 6.0 times 10 to the power of 24 kilogram. You also have a constant G, 6.67 times 10 to the power of minus 11 Newton meter squared over kilogram squared. And you have a satellite which traveled around the Earth in 24 hours, so a period of 24 hours. And they want you to find the distance in which the satellite is high from the Earth. So let's call this h. This is the radius of the Earth. They want to find h. You have the formula net f equals ma, and since we want to find the radius, we change this to v squared over r, or the height, not the radius. So you have f equals m times v squared over r. This is also equal to g times m over r squared. So we have g times m over r squared is equal to m v squared over r. If you solve for v, you'll get v squared is equal to gm over r, and the velocity is generally displacement over the time. You already have the time is 24 hours, which is d, and the displacement of it is the earth, which is the circumference of the earth, so it's 2 pi r. So you have 2 pi r over d all squared is equal to gm over r. Both of these are, they're equal to the height, which is the satellite from the surface of the earth, plus the radius of the earth. If you solve for r, or for h plus re, you'll get r cubed is equal to gmt squared over 4 pi to the 4. So you substitute the third root of 6.67 times 10 to the power of minus 11 times the mass of the earth, which is 6.0, times 10 to the power of 24. D is 24 squared over 4 pi to the 4, and then this minus the radius of the earth. That's what h is equal to. You will get h is equal to 3.6 times 10 to the power of 7 meters. For basic question 3, you have the moon and you have a satellite 80 kilometers above the moon. It's orbiting the moon. They want you to find the period in which it orbits the moon once. So we can use the formula, and at f equals ma, and we substitute for a v squared over r, because we want to find the period. So it's m v squared over r is equal to f, and this is equal to g times m times the mass of the moon times the mass of the satellite thing over r squared. So you'll have g, the mass of the moon, the mass of the satellite over r, so small m over r squared, r total. So it's the radius from which the objects from the moon plus the radius of the moon is equal to m v squared over r. So from here you can solve for v squared. You will get v squared is equal to g, this is the constant g, 6.67 times 10 to the power of minus 11 times the mass of the moon. They gave it to us, it is 7.35 times 10 to the power of 22 kilogram over the total r. Which is the radius of the moon. They gave us this 1.74 times 10 to the power of 3 kilometers plus the height, which is the satellite from the surface of the moon, which is 80 kilometers. You can substitute for v 2 pi r. The total r, this would be the radius of the moon plus the height, over t all squared is equal to gm over r. You can solve for t now. You will get t squared is equal to 4 pi squared, the total radius, this one, r to the power of 3 over g times m. So t will be equal to radical 4 pi squared r, which is the radius of the moon, 1.7, 4 times 10 to the power of 3 plus 80 power of 3 over the constant g, 6.67 times 10 to the power of minus 11 times the mass of the moon, which is 7.35 times 10 to the power of 22 kilograms, and you will get 1.94 hours. So for basic question 4, you have the earth, the radius of the earth, and you have the mass of the earth, a constant g, and you have a satellite above it. Its period is 150 minutes. They want you to find this at this distance. So we derived the equation from one of the previous basic questions. You can just use the equation directly. This h, which is over here, is equal to the third root of the constant g times the mass of the earth times the period squared over 4 pi squared minus all of this minus the radius of the earth. You can just substitute directly 6.67 times 10 to the power of minus 11 multiplied by the mass of the earth, which is 6.0 times 10 to the power of 24 kilogram. The period they gave it was it's 150 minutes. 2 hours, you will get it's 2.5 hours squared over 4 pi squared, and then this minus the radius of the earth. They gave it to us, it is 6.4 times 10 to the power of 3. You will get h is equal to 2.96 by 10 to the power of 6 kilometers. That's part A. Now part B, they want the speed of the satellite. We also derived the equation from this in one of the previous basic questions. The formula for this would be V equals radical G times M over R, the total R. So it's the h, the distance from which the satellite is from the earth, plus the radius of the earth. So 6.67 times 10 to the power of minus 11 multiplied by the mass of the earth. This is 6.0 times 10 to the power of 24 kilogram over the total radius, which is 6.4 times 10 to the power of 3, plus we got this h from part A, it is 2.96 times 10 to the power of 3, the root of all this, and you'll get the speed of the satellite 6.54 times 10 to the power of 3 meters per second. Now part C, they want the angular speed. You can use the formula V equals R, the linear speed equals R times the angular speed, omega. So omega is the linear speed over R. The linear speed from part B, it is 6.54 times 10 to the power of 3 over the total R, which is 6.4 times 10 to the power of 3, and from part A 2.96 times 10 to the power of 3, and you will get 6.99 times 10 to the power of minus 4 radians per second. Okay, so for basic question 5, we have the Earth with its radius 6.4 times 10 to the power of 3 kilometers, and you have the mass of the Earth 6 times 10 to the power of 24 kilogram, and you have the constant G 6.67 times 10 to the minus 11. And you have an object which is lifted from the surface of the Earth to a distance above the Earth. This distance is 1.6 times 10 to the power of 3 kilometers, and the mass of this object is 4 kilogram. They want you to find the change in the potential energy for this object. So you do U final minus U initial. The formula for U is minus G M over R squared. For the final, this R would be the radius of the Earth plus the H, this H, but for the initial it would be just the radius of the Earth. So U final is minus 6.67 times 10 to the power of minus 11 multiplied by the mass, which is 6 times 10 to the power of 24. That's the mass of the Earth, and then you have the mass of the object, 4 kilograms over. So for the final, the radius is 6.4 times 10 to the power of 3 plus 1.6 times 10 to the power of 3. For the U initial is also minus 6.67 times 10 to the power of minus 11, 6 times 10 to the power of 24, 4 kilogram for the object, and then 6.4 squared times 10 to the power of 3 squared. So you can subtract them. U final minus U initial, and you'll get 5 times 10 to the power of 7 joules. So for basic question 6, you have Earth with its radius and the mass of the Earth. The radius is 6.4 times 10 to the power of 3, and the mass 6 times 10 to the power of 24. This is kilometers and this is kilogram. You also have the constant G, 6.67 times 10 to the power of minus 11, and the unit is Newton meter squared over kilogram squared. For part A, they want you to find the kinetic. Also, you have a satellite, 50 kilogram satellite, mass is 50 kilograms, and it is at an altitude of 1.6 times 10 to the power of 3. They want you, for part A, we want to find the kinetic energy of the satellite. The formula for kinetic energy is G mm over 2r, 6.67 times 10 to the power of minus 11 times the mass of the earth, 6 times 10 to the power of 24, the mass of the satellite 50 kilogram, 2 this is the total radius of the earth plus h. The radius of the earth is 6.4 times 10 to the power of 3 plus the altitude, which the satellite is above the surface of the earth, that's 1.6 times 10 to the power of 3, and you will get the kinetic energy to be 1.25 times 10 to the power of 9 joules. For part B, they want the total mechanical energy, which is the kinetic energy plus the gravitational potential energy. Formula for kinetic energy Gm m over r 2r. Formula for gravitational potential energy minus G mm over r. You will get minus half times Gm m over r as the formula for mechanical energy. You can substitute minus half by 6.67 times 10 to the power of minus 11 multiplied by the mass of the object, 6 times 10 to the power of 24 multiplied by the mass of the satellite, 50, over the total r, which is 6.4 times 10 to the power of 3 plus 1.6 times 10 to the power of 3. You will get minus 1.25 times 10 to the power of 9 joules.
B7. Assume the earth and you have a man standing on it. He's not moving, he's just standing. Total mechanical energy is just the potential energy. Now, what's the potential energy of the man? Normally, if you took your U point to be somewhere near you, like let's say 2 meters below you, then you just do mgh, but this is a separate formula because you're using it relative to the earth. So relative formula is minus G m over r. So this is just the general formula for any potential energy. And then G is a constant, m is the mass of the earth, small m is the mass of the man, and r is the distance between the center and the man. Let's check it. Yes, it's there. Now, what's the total mechanical energy at an infinite distance? Now, we said that it's minus Gm m over r. Now, what if r was really far away, like infinity? So as r approaches infinity, this will get really big denominator, which means it will make the whole thing closer and closer to 0, where theoretically, if it was infinity, it would be 0. So it would be 0. It approaches 0. What is the binding energy of the man? The binding energy is the energy that is keeping it on Earth. So it's basically the potential energy between the man and Earth. Now, is it positive or negative? It's positive, because you need delta U. Like, what if he was free? You need to compare it to if any forces weren't exerted on him. So you do that minus the potential energy, so the minus and minus cancels out. So binding energy is just minus the mechanical energy. or just minus the potential energy. What is the escape velocity? The escape velocity is basically how much speed does he need to get out of this atmosphere, the gravitational atmosphere. So what happens is you use the gravitational potential energy and you equate it to the kinetic, because that's how much kinetic energy you need. Basically K plus U equals 0, and then U is minus, that's why it works out. So half mv squared is equal to U, which is G m over R. M and M cancel, then you get V is equal to square root of 2gm over R. Now notice here there is no mass. Now you just substitute the variables, you should get it. Since there is no mass, what's the escape velocity of a 10-gram ping pong ball? It's the same thing, because there's no mass. And they said in kilometers per second, so whatever answer you get, divide by 1000. Divide by 1000. Also make sure this is in meter. That's it for B7. Now B8. Find the potential energy at an altitude RE above the Earth. So potential is minus GM M over R. Now R is 2RE. So 2RE, you substitute the values and you get it over there. I'm sorry I'm doing it over the Azan, but I recorded it. It's starting, so at an altitude 2RE above the surface of Earth. So same thing again, minus GMM over RE plus 2RE, because you have the first normal and then you have the one altitude. Deduce the energy required to lift the 5 kilogram body from altitude RE and altitude to RE. Simply, it's the difference between those two, between A and B. So you get the difference, and then how I like to do it is to find out if it's positive or negative is, do you need energy to make it go more up? Yes, you do, because rocket fuel, for example, you need energy in the rocket fuel, in the chemicals, to send it up to space. Otherwise, you could have, like, the opposite direction. Let's say you want to go down. If you had a hole, you could have just dropped it in and the potential energy would drag it down. So it's basically, you give energy to make it go up. So from altitude RE to 2RE, it's positive. So difference of those two, but positive. There you go, it's positive. And if the 5 kilograms is dropped from altitude 2RE, find the speed here. If you just drop it, so you had a higher altitude and you just dropped it, then you would gain energy, you would gain speed. So whatever change you got here, it's equal to half mv squared. And you plug in m, 5 kilograms, and you get v. You do radical of that, you get v, and divide by 1000 because kilometers per second. That is basically it. Faisal will do BQ9.
For basic question 9, you have here's the sun and here's the earth. The radius of the orbit of the earth around the sun is 1.5 times 10 to the power of 11 meters. And you also have the time of the orbit, 365 days. They wanted to calculate Kepler's constant. So the formula for Kepler's constant, K, equals the radius to the power of 3 over the period squared. The radius they give to us 1.5 times 10 to the power of 11 meters, all cubed, over here, just 365 days. We have to convert it to seconds because the SI, so it will be 24 hours per day, and then 1 hour 3600 seconds. All of this squared. You should get 3.39 times 10 to the power of 18 meters cubed per second squared. This is Kepler's constant.